We're going to be looking at identify basic facts about radio frequency spectrum. Again, this is the KPC measurement. You have to get 70% on the KPC in order to go to well, next module. The AFSC application. I cannot emphasize this enough that you will probably get barraged with frequency ranges all over the place. There are a few out there. We just want to point them out to you. We're not about trying to get you to memorize every one of them because it's possible. But there are a set of frequency ranges that we need you to be very aware of, and there are some questions being asked with them in this particular objective. We're going to be looking at frequency bands, frequency characteristics, the electrical length, and physical length. So we're going to be looking at three different types of radio frequency bands that are out there. Some of them overlap, some of them align, and that's what we want you to be aware of. We're going to show you what we as the military pay attention to. So we have the medium frequency, which is normally the 300 to 3 megahertz. This is all the military side. We have the high frequency 3 megahertz to 30 megahertz. Now, why are we pointing this out to? Well, if you take a look at these three here, you have the IT, International Telecommunication, and the IEEE. Normally, those two ranges are identical, but NATO changes them. So if you're going overseas, you need to be aware of that NATO has different designations for frequency. And that's the reason why we are giving them to you as, okay, be aware of these. These are the ones you need to pay attention to. See this a lot in the several blocks or several modules that you're getting ready to go through. We also have VHF, very high frequency. It starts from 30 megahertz, goes to 300 megahertz. We have ultra high frequency from 300 megahertz to 3 gigahertz. And you have super high frequency SHF, which is 3 gig to 30 gig, and extremely high frequency from 30 gig to 100 megahertz. Now, you'll notice that when we get into the Satcom bands, a little bit different. It changes. So when we see something like C band, it's 5.85 gig to 8.20 gig. X band is from 8.2 gig to 12.4 gig. And then we have KU band, which is 12.4 to 18 gig. And then KA band, which is 26 to 40 gig. Now you'll notice that we have the KU, which means under the K band. Then we have KA, which means above the K band. Down below in that note shows you, hey, this is the K band. Your module that has the GMT in it, those are the four sets of frequencies you're going to be dealing with. C band, the X band, the KU, and the KA band. So when we look at radio wave propagation, they all play a part in these frequencies. So let's take a look. There's two basic types, your ground waves and sky waves when we propagate. Now, the antenna, what is it going to do as far as going the distance? Ground waves, pretty much what it says. It's all on the ground. You've got direct waves, and the big thing on direct waves is space waves is included in it. NASA has come out and said that direct waves are space waves and space waves are direct waves. Ground reflected waves and surface waves. So let's take a look at the first one. Direct waves are normally at what we call line of sight. It means that if I can see your antenna optically, I should be able to transmit and receive each other. Space waves, again, line of sight, usually associated with radar and Satcom frequencies. I do want to point out that there is a difference between regular line of sight by certain antennas versus a direct line of sight. We'll get into that later. But right now, line of sight means that if I should be able to see that antenna, be able to reach it. This gives you an example of a line of sight. Can I see it? Yeah. Just the higher up I can get, the more direct I can get to you. We also show you that the space waves going, that's on the left-hand side of this diagram, going right out into space, that are normally for radar and your Satcom. When we look at the other direct waves, we've got ground reflected. Just like it says, it's going to reflect off the ground. The problems with some of these ground reflected waves is you got something called echoing or fading, which makes the signal sound like it kind of dies out and then comes back. That's because you have a lot of multipathing in there. Now, more of your better radios compensates for it, and you have a steady signal all the time. Here gives you an example of a reflected wave that's bouncing off the Earth. I think in your study guide workbook it shows you also some types of reflected waves. We look at surface waves, which are electrically coupled to Earth. Now, this one may travel farther than where the eye can see. And that's because the magnetic field and the frequency are basically hugging, and when it dissipates to dissonant, in other words, it's power, because as you go out, it starts getting weaker and weaker. So there will be a place where it stops. This gives you an idea of a surface wave where it is hugging the surface electrically. Let's look at skywaves, the other part of this story. So with skywaves, it'll be either refracted or reflected. We'll talk about that later off of the ionosphere. The ionosphere is another point in our lovely, wonderful RF world. Normally, our communications are both the ionosphere and troposphere, in where we do most of our communication. It is considered beyond line of sight, and normally it's in the HF region, but you can see that 2 to 30 megahertz. 2 is actually in the medium frequency area, and then the 3 megahertz and up is in the HF area. With skywaves, the whole idea is it's going to refract off the ionosphere. There is this little thing called a skip zone. In other words, where the ground waves stop and the sky waves don't return back to Earth yet. It can be shown in these two pictures. One is the sky waves. It's showing you the yellow arrows with the space wave. That's a direct line of sight. But it also shows you that the ionosphere with the red arrows showing it is refracting or reflecting off of ionosphere. This gives you an area where the skip zone is. Again, the ground wave stops. The place where the sky wave has not returned back down to Earth, that whole area is called the skip zone. Or as anybody watch Jeff Dunham? No? You know, you remember Ahmed the Dead Terrorist?
A little bit.
Silence. There you go. Yeah, that's the
Oh,
cone of
that's right.
silence, so to speak. And of course, this gives you an idea of there is these little things that the ionosphere does. For example, that HF area of 2 to 30 meg, your higher frequencies are best used during the daytime. Your lower frequencies are best used at nighttime. When you take a look at it, you're going to get a lot of distance by knowing that and understanding what the ionosphere does, which should be covered in the next objective. We have medium frequency. Again, we're going back over it, this time identifying where they fall into. For the most part, medium frequency falls into the ground waves. However, the higher up it goes, it starts the capabilities of being able to go beyond line of sight and even what we call over the horizon. Has everything to do with what's happening in the troposphere and the ionosphere. Then you have HF. This is your ground waves and beyond line of sight. So if you have a small transmitter, then ground waves is the way to go. If you have a little bit powerful transmitter, you can go pretty far distance. And it has everything to do with the frequency, the time of day, antenna that you have, and we'll get into that later. You have high frequency. This is your 30 to 300 meg. This is primarily used for line of sight. And then when you start getting into the UHF, this is where it could be used for over the horizon on a consistent basis. When you get into SHF, though, that's at 3 to 30 gig. You got line of sight, over the horizon. And again, that is more your lower SHF frequency, somewhere around that, all the way up to about 15 gig. It does cover on your line of sight the Satcom band. And then lastly, you have your EHF, your extremely high frequency. This is strictly line of sight. I think there's a place in your study guide workbook that talks about it. There's nothing out there. What is the farthest that it can go? And it says like 2.5 miles or 2 miles or something to that extent. This is that little Satcom band. Of course, those 2-3 miles or whatever it is talking about, that's if it was just transmitted in a vacuum, I think, and a couple other factors in there. There's nothing that's going to impede it. But we all know that there's a lot of environmental factors down here on the Earth, and voila, it's going to transmit it up into the atmosphere. So we got to give it a little bit of punch. That. Now, there are plenty of electromagnetic charts. This gives you an idea. Your VLF, that's very low frequency. We do use that, but that's more along the lines of the Navy. Then you have the lower frequency, your AM signals, getting into the medium frequency, your shortwave radio like the HF, the VHF television, FM radio. If you get over the air, it starts around the 200 megahertz area. And this is your TV. And then when you get up into the UHF area, it ends about 800 megahertz. You also get GPS, Wi-Fi, 4G, along those lines. And then SHF, you got Satcom, and EHF, that's at radio astronomy, along with your more sophisticated Satcom communications. When we look at electrical length, this is defined as the length of a wave as it travels through a new medium compared to free space. In other words, an antenna. The electrical wavelength, or electrical wave, try that again. Electrical length is measured in wavelengths. It is a fictional thing, but we need it for theory so we can apply it to a physical. Now, an antenna is going to have more resistance in air, therefore the wave's going to travel a little bit slower through the antenna. That's obvious because of the resistance. When you calculate electrical length, breaking it out for you, so there will be a KPC that gives you some information on how to do it. This gives you the overview. We have C, which is the speed of light. Normally it's in meters per second. You have frequency, which is in cycles per second. And then you have the wavelength in meters. So when you take a sample frequency, for example, I'm giving you 30 megahertz. Well, speed of light is basically 3 million meters per second. Then you have 30 million hertz. And when you divide those, you end up with 10 meters as the electrical length. That's what the antenna thinks it is going to be, is 10 meters. How long is 10 meters? Well, I know for a fact that 5 meters is 16.7 feet. So you're looking at what, 33 feet, somewhere in that general area? So that's 33 foot for an antenna. That's going from your radio to the antenna. Nothing in between. And that's theoretically. When you get to the calculation of physical length, in other words, how long is that antenna going to be when I tie it to cable and everything else, has everything to do with the length of the conductor, what the gauge of the wire is, and how long the cable is. So when we look at this, we're hoping that everything is 12 gauge wire. That's where the standard is. But we know that if we change the diameter of the cable or the antenna, for example, if you don't have a 12 gauge solid core wire for your antenna, well, believe it or not, speaker wire works. So it just gives you an avenue of what you can use out there. So normally when we look at wavelength, theoretically and from the electrical part, physical length is actually going to shorten that antenna. Let's take a look how. Physical length is measured in any length. You take out the tape measure, most of ours, because we have the imperial system in the United States, it's measured in inches, feet, yards, miles, so forth and so on. Whereas the metric system is, you're dealing with meters, kilometers, so forth and so on. The one thing that we are going to add in there is something called a velocity factor. That is the cable. Again, cables is going to be a different medium versus what that medium is, the wire you use for your antenna. The way this works is the calculation is pretty much the same as the wavelength, just you're adding in velocity factor. Again, we're going to use the 30 megahertz. Again, we're going to calculate for our electrical wavelength, which is 10 meters. Now we got to find the velocity factor. Now, I included this particular device in here. You can find this all over the internet. This one came from FEBO reference, and this is a chart on some of the common cables we use. And when you take a look at it, we're going to be using either the RG58, which is a common 50 ohm cable that we have, or the RG213, which again we use in the shop. You'll notice that it says 66.0 on both of them. So it won't matter which one we use. We know it's going to be 60.0. What does that mean? Velocity factor is 66.0. That's 66%. Yeah, 66%. So let's get to the calculation on physical length. This is 30 megahertz. We found the electrical wavelength, which is 10 meters. Now I got to find the velocity factor, which we're going to use either RG213 or the RG58, which is at 66%. So we end up 66% times the 10 meters that we got from our electrical length, and our physical length with 100 feet of cable, because if you look back on our velocity factor and loss data per 100 feet, you will see it says 100 feet. That's pretty much what every cable I have seen when it comes to velocity factor. So in this case, our actual antenna with the cable has to be about 6.6 meters for that frequency. Kind of crazy with all this electrical length. So just remember, when we are looking at electrical length versus physical length, electrical length is a signal in what it thinks it wants to be, and it's measured in wavelengths, versus a physical length. In other words, you're touching it, you're putting a yardstick or some type of ruler or whatever it is to it, And that is going to be measured in either meters or feet, depending on what you got. Now, with me, I like to do, like I said before, the sync the lights to music. I actually have a homemade antenna on my antenna mast that I use to transmit out my frequency. And I compensated the cable with the antenna. My antenna is approximately 6 feet long, but it's actually 3 feet on one side and 3 feet on the other side. And you're going to understand it when we get into something called a dipole. Last up, again, we've looked at frequency bands and characteristics, calculate electrical length and physical length.